Okay, so we all hear about the amazing things AI can do, right? From writing code to creating art, it's everywhere. But there's a hidden cost, a massive energy footprint that's starting to pop up in a place you really might not expect, your monthly power bill. Let's dig into how that's happening.
And you're probably thinking, wait, what does some chatbot on the other side of the planet have to do with the lights in my house? It's a totally fair question. The answer, well, it lies in the incredible and frankly, fast accelerating demand for energy that's powering this whole AI revolution. And here's the number that really puts it all into perspective, 12%. It's projected that by 2028, data centers, which are being driven more and more by AI, could eat up to 12% of all electricity generated in the United States. That's a massive, massive slice of the entire nation's energy pie. To really get a handle on this, we got to look at the numbers. And we're talking about energy on a scale that's, well, it's kind of hard to imagine. It's measured in what are called terawatt hours. For context, just one single terawatt hour is enough to power about 90,000 US homes for an entire year. Yeah. This timeline here tells a pretty powerful story. So back in 2014, US data centers used about 58 terawatt hours. By 2023, that number had already tripled. But now look at the projection for 2028, a potential leap to as high as 580 terawatt hours. That isn't just growth, people. That is an explosion. This graph shows you just how steep that climb really is. You can see the steady rise up to today, and then, boom! That giant shade of area shows the future we're projecting. It's like we are standing at the bottom of a very, very steep mountain of energy demand. And hey, this isn't just a US issue, not at all. The International Energy Agency projects that globally, data center demand is going to more than double to almost 1,000 terawatt hours by 2030. And the main reason for this crazy surge? Yep, you guessed it, AI. So, here's the crucial question. What does all this immense pressure on the power grid actually mean for you? How does it go from being these enormous abstract terawatt hours to actual dollars and cents on your bill? Well, it comes down to a concept that's called a rate pressure wedge. Now, think of it this way. All this new demand from data centers gets layered right on top of our existing electricity needs. That extra layer, that wedge, it puts a ton of strain on the entire system, and that can drive up prices for everyone. This chart here illustrates what that pressure could actually look like in your wallet. It shows 3 different scenarios, basically modeling what happens if this demand adds 1, 2, or even 3 cents to the price of every single kilowatt hour of electricity that you use. Let's break these numbers down. In that high-end scenario, adding 3 cents per kilowatt hour could mean an increase of almost $26 a month for the average US household. And in a state like Idaho, where homes tend to use a bit more electricity, that number climbs to over $28 a month. That's more than $300 a year. Let that sink in for a second. That's a potential extra $26 or even more tacked onto your bill every single month simply to power the immense computational needs of this AI boom. So, is this future of rising bills just inevitable? Well, not necessarily. There are ways to bend the curve of this energy demand, using solutions that range from the pretty practical to the downright futuristic. Okay, on the practical side, we can be a lot smarter about managing the grid. This means things like building new data centers near clean energy sources. It means using long-term agreements to lock in stable energy prices. And it means getting big users to scale back during peak hours so they don't strain the grid for everybody else. But what if managing the grid better isn't enough? What if we have to completely rethink computing itself? This quote from Claire Fitzpatrick at Boise State University really gets to the heart of a radical idea. I mean, our brains are unbelievably powerful and efficient computers. The big question is, what can we learn from them? And this leads us to the cutting-edge field of organoid intelligence. And yes, it absolutely sounds like science fiction, but it's really happening in labs right now, with the goal of completely rewriting the rules of energy-efficient computing. So, what is it exactly? Well, researchers are creating these things called organoids. They're essentially tiny, simplified organs from human stem cells. These organoids then grow into dense neural networks, almost like a miniature brain. And the goal is to harness their natural biological efficiency for computation. The contrast here is just stark. Traditional AI relies on these massive, power-hungry data centers,
Organoid Intelligence, on the other hand, it leverages the biological hardware that nature has spent billions of years perfecting. It's really the ultimate quest to do more with less.
So how do you even measure this stuff? It's fascinating. First, researchers cultivate these living neural networks. Then they build an electronic interface to communicate with them. And here's the really brilliant part. They also create a digital twin, a perfect computer simulation of the organoid. This lets them run the exact same task on both the biological system and the digital one and compare the energy used, right down to the joule per task. Of course, this kind of research raises some huge ethical questions, and the scientists are tackling those head-on. They're working with ethicists and global experts to establish really clear boundaries, making sure this science proceeds responsibly right from the very beginning. You know, it all comes back to this one simple idea. The cheapest, cleanest kilowatt hour is the one you never have to use in the first place. Whether it's through smarter grids or revolutionary biological computing, efficiency is the ultimate goal here. So as we look at that ever-steepening curve of energy demand, we're left with this one profound question. Could the solution to AI's immense appetite for energy be found not in building bigger and bigger power plants, but by looking inward to the incredible efficiency of living biological cells?